Welcome. I am Mrinmay from Computer Science Department, Haldia Institute of Technology, and right now I am going to discuss on IPv4 logical addressing. And here, the logical addressing is mainly the function from network layer. And logical addressing, as it is the function of network layer, other than because it is fully associated with communication, and network layer is responsible for host to host communication, whereas transport layer is responsible for process to process communication, and IP addressing is playing the major role in case of communication. And here, other than logical addressing, as we are talking about the logical addressing, definitely in contrast, there is another addressing concept which is physical addressing, and here it is beyond of our scope as it is associated with the data link layer, the physical addressing, and logical addressing, and more precisely, we are going to discuss on logical addressing with IPv4 because there is another version of IP which is IPv6, and I am not going to discuss on that. And with IPv4, we are having 32 bits to represent an IP address. And basically, most of us, we are familiar with this kind of notation of an IP address because nowadays almost all we are doing well with the smartphone and all the smart devices, and everywhere whenever there is a smart device connected with the network, definitely it will have an IP address associated with this. And with IPv4, this particular type of IP representation is known as dotted decimal notation. Although we are talking about 32 bits IP addressing, and here you follow, that is, here is 8 bit, here is 8 bit, another 8 bit, another 8 bit. So 4 into 8 altogether 32 bits. And whenever we are representing a byte with the corresponding decimal, then it is known as dotted decimal format. And in this way, we are getting our dotted decimal notation. And here to clarify more detail, so we have taken an example, and here all the binary presentation of IP address is given, where our task is to convert the binary address into corresponding dotted decimal notation. Here it is easily found that 100000001, so which is mapped to 129, and in similar fashion the rest of the bytes which are converted to corresponding decimal equivalent, and in this way, and each the bytes, they are separated with a dot, that's why the name dotted decimal. And another example we have considered here, and here mainly that is how we will consider an IP address in network. Basically, so all these are not the valid IP addresses. As we will discuss, then we can follow that is what's wrong in it. And in case of the first example, if you follow the third bytes, the third octet, it's having a leading 0, which is not considered in case of IP addressing. So that's why it's a wrong representation of an IP address. And in case of the second one, the number of decimal equivalent octets should be exactly 4. So here you follow, we are having 5 octets, which is not allowed because each octet is equivalent with 8 bits. So 5 octet means 5 into 8, that is 40, which is violating the rule of IPv4, where it is considering only 32 bits. For the third one, so the clarification is each decimal equivalent octet need to be less than or equal to 255. And why it is? Because if we consider any 8 bit, then the maximum binary number we can represent with the 8 bits is 8 ones, which is equivalent to 255. So anything which is more than 255, so that is violating the rule. So that's why here in case of the third one, here we can see there is another one octet which is 301, which is violating the rule. So we will not, definitely will not consider the third one. In case of fourth one, so here it is clearly we can see here is a mixture of the binary as well as the decimal equivalent, which is strictly prohibited. Now, amongst the IP addressing, so whenever as we are going to represent an IP, then there must be some classifications according to the use of the IP addresses. Because we know in a case of addressing, there is unicast addressing, there is multicast addressing. And what is unicast addressing? When one-to-one mapping, that is one-to-one communication is required, then we'll go for unicast addressing. And when one-to-many or many-to-many addressing is required, then definitely we'll go for the multicast addressing. Here, and according to this IPv4 with class full addressing, there are mainly A, B, and C which are responsible for unicast addressing. That is when we are going to address a single host. Now, how they differ? So we are coming later. And D is used for multicast addressing, where our recipient is multiple number of receivers, and E is reserved here, is not used with this IPv4 addressing. And the speciality of this addressing is the class A. How we can identify a class A, class B, class C, and what is their use? And actually, class A, there the first byte is the network address, and the rest 3 bytes are the host address. It is a two-level hierarchy. The first higher level hierarchy, which is recognizing or identifying the network, and the rest portion is recognizing the host itself. In case of A, the first byte is responsible for network, and similarly, in case of B, the first 2 bytes are responsible to identify the network, and the rest 2 bytes are responsible for recognizing the host. In case of C, the first 3 bytes for net ID, the last byte is for host ID. And each of these classification are having their merits and demerits. And from this figure, it is clearly visible that as the 3 bytes are responsible for host, definitely the number of IP address is more with the class A. Number of IP addresses in class B is medium, and number of IP addresses in class C, which is less. And so here are the utilities for class A, class B, class C, like this. And the speciality of this class is that with classes, how we will recognize whether it's class A, whether it's class B, whether it's class C. If any address starts with 0, then it belongs to class A. And side by side, here the range of the each of the class is defined there. That is anything if as the first byte is responsible and the 0, it is started with 0. So if all are the ones, then the maximum number will be how much? 127. So that's why the maximum range is 127. And we may have all zeros. So that's why the beginning range is 0 and the maximum is 127. And in similar fashion, for class B, for easily recognition, we will recognize the first 2 bits 10. If any address starts with 10, then we will recognize it as class B. And for class C, the first 3 recognizing bits are 110. For class D, it will be 1110. For class E, it will be 4 consecutive ones, first 4 bits. And here the ranges are given there: 0 to 127, 128 to 191. The blocks, these are the blocks. Because maximum we can proceed up to 255. high. So whatever blocks, so that will lie in this range. So first 0 to 127, it is belonging to class A. The next 128 to 191, it is belonging to B. Then 192 to 223, it is belonging to class C. Then 224 to 239 belonging to class D, and 240 to 255 it is belonging to class E. And here more detail is given there. Say for the first block, the address should be 000 because first bit or first byte always it should be 0. For the rest 3 bytes, the beginning range is 000 and the final range will be 255, 255, 255. So this is for first block, 0th block. And as we will proceed, we will see the next block starts with 1. So the beginnings are 000 and it ends with 255, 255, 255. So in this way, we will derive all the ranges for all the blocks, and the last block is the 127 block, and its starting range is 127.0.0.0 and ending range is 127.255.255. And along with this, there is another concept which is mask. Mainly, masking is done to derive the network ID for any given IP address. So for the class A, as we have considered the first byte for the network, for recognizing the network, so the mask should be 255.0.0.0 because the rest 3 bytes, they are responsible for identifying the host. So if we perform the AND operation with any given IP address and this mask, then we will derive the net ID. And here, for the rest of the classes, the ranges are given. So as we have discussed earlier, so here just explanation is given nothing else. That is, any address starts with 10 and the first 6 bits are 0000000. So it is 128. If we put all ones, that is the maximum range, we will get 128 plus 63 and which is 191. So this is the range for class B. And in similar fashion, we can derive the range for class C as well because we know the trick already. That is, what is the trick? The first bits, which are the reserved bits for any class. As we have seen for class B, it was 10. For class C, it will be 110. So if we consider the rest 5 bits, so initially we will start with definitely all zeros, and finally we will have all ones. So if we put all ones, only along with 192 we have to add 31 blocks more. So which leads to 2 to 3. So this is the range of class C. And in similar fashion, we can find the range for class D, class E as well. Along with this, here the default masks are also given for class B. And already we have told that is the first 2 bytes are responsible for network ID. So that's why the first 2 bytes will make them 255, 255, which is the default mask. That is any IP given from class B. So their network IP or ID can be derived performing the AND operation with this mask. The same is applicable for class C as well because there we have seen the first 3 bytes are responsible for net ID. So that's why 255.255.255.0 it will be the default mask. And here one example is given, that is how to find a network address. That is, if any IP is given, here you follow. Here the IP address is given this one. Although it is the binary equivalent, and we can find out its dotted decimal equivalent as well. So as our task is to perform the AND operation, bitwise AND operation, that is, this is the mask you can follow. This is 255.0.0.0, which is default mask of A. because this IP is belonging to class A because its starting bit is 0. So that's why we'll choose the class A default mask. And we are performing the AND operation, bitwise AND operation, and we are getting 99 because if we convert this binary to its equivalent decimal, we'll get 99. So that's why the network address will be 99.0.0.0. And here is another example, that is how to find the class of each address. And the trick is already discussed, that is any address started with 0, that will be class A, and accordingly you can see the result. And the first two bits are 1, 1, 0, so it will be belonging to class C. And here you follow, it is decimal equivalent, dotted decimal equivalent, and we know the range. For class A it will be 0 to 127, that's why 14, it is belonging in that range, so definitely it will belong to class A. And you follow, that is the range we know, from 240 to 255, so that range is belonging to class A, and that is the result. It is quite easy if we know the ranges. And here number of blocks and block size in classful IPv4 addressing. And here you follow for class A 0 to 127, the total number of blocks including 0, it will be 128. And block size, how block size is calculated? And it is nothing but the number of hosts in the particular block. As we know, there are 3 blocks or 3 bytes which are responsible to represent the host, and it will be definitely 3 bytes means 24 bits. So how many addresses will be there? 2 to the power 24 bits, and here is the equivalent number of 2 to the power 24. This number of addresses are there in each block. And what is the purpose of this? Already I have told you. So first 3 classes are used for unicast, and D is used for multicast, where E is belonging to reserve. And here, as we are talking about this unicast or multicast IPv4 addressing, the major demerit of this is that is most of the IP addresses, so they are wasted. Why? Because if we consider any organization, so how many IP addresses are may be required? A big organization, it may require 1,000, 10,000, lakhs, but if you follow the block size, so it is much more than that. So simply it is wasted, nothing else. So nowadays it is obsolete. And how we can recover this? That is what will be the remedy to this? Definitely we will have another approach, and we are coming later with classless addressing. And before that, here is the number of blocks and the block size for each of the classes, and some observations. That is, it is very large. We are just right now discussing over this. And B is also very large because 2 bytes are responsible for host, and whereas comparatively C is having small size. And here you follow the last point. It is talking about the another kind of notation, which is CIDR notation, classless interdomain routing, and where the 4 along with the dotted decimal with a slash and n, we will represent this notation, where slash n, it is defining the mask. And how it is working, when we'll discuss a problem, so then we'll see how it is working. And some more observations, that is the number of addresses in the block can be found by using the formula 2 to the power 32 minus n, where definitely n is the number of bits available in the mask. And first address for any block, whenever we are given any block, actually ISP, internet service provider. So they used to assign the block, and whenever they are assigning the block, then how we will, our first job will be how many addresses are there, and what will be the first address, what will be the last address, and we can derive all the addresses. That is, if we are able to count the number of addresses in the block, then definitely we'll be able to find all the addresses in the block. So once we know the first address, definitely we can move to second, third, and so on, and accordingly we can move to the last address as well. And there is a easy trick, and the trick is just find out 32 minus n, where n is the mask, number of bits in the mask. Then once we have got like this, then replace all these number of bits with 0, and it should be done at the last byte. And in the similar fashion, if we replace 32 minus n number of bits with ones, then we'll get the last address. So with replacing the zeros, we are getting the first address. Replacing with ones, we are getting the last address. And this thing, whatever we have discussed right now regarding the mask and the number of addresses in a block, first address, last address. So with an example, we can clarify it more clearly. And here the example given 205.16.37.39/28. Definitely this one is the mask. And here the question is, how many addresses are there in the block? These are very common. Whenever we are going to design any network, then these will be our task. And what will be the first address and what will be the last address? The number of addresses in the block can be found by using the formula 2 to the power 32 minus n. And now what is n? It is known to us. So easily we can find, that is just I am going to the previous slide. Here the mask is /28. Definitely n value is 28. And once we are finding 32 minus 28, it is done in the next line. So 2 to the power 32 minus 28, it is equivalent to 2 to the power 4, which is equivalent to 16. So it is clear that 16 number of addresses are there. And now we are coming to how to derive the first address. And here, as we talked about the reduction of the number of n from the 32. So 32 minus 28, so 4. So rightmost 4 bits should be replaced with 0 to get the first address. So as we are replacing the rightmost 4 bit with 0, then we are getting 205.16.37.32, which is the first address. And the block we have given, it was 39 in follow. So 39 is equivalent to this one, 32 plus 7, 111. But here we are replacing the last 4 bits with 0. So as we are making the last 4 bit 0, so this bytes becomes 32. So 32 will be the first address of this network. Now, how to find the last address? The same trick will apply here. That is, again we will find 32 minus n, where n is 28 and it is 4. So the last 4 bits should be replaced with all ones. And once we are doing so, we will get 47. So from here, we are getting the last address of this block. And here is the pictorial representation. Whatever I have derived till now for the given example, that is, this is the first address, this is the last address, and if you count 32 to 47, it will be 16. So we know 2 to the power 32 minus 28, it is equivalent to 2 to the power 4, which is equivalent to 16. So 16 number of addresses are there in the block. And here is some handwritten derivation, and I am doubtful whether it is clear or not, but I'll try to make it clear. Actually, it is given the network IP is given 192.168.1.1 130.0 is using the subnet mask 255.255.255.224. Now question is, how many subnets are there in the network and what are the ranges of each network? And our first job is to convert the given mask into its equivalent binary. And as all the first 3 bytes are 255, so it is quite easy because we will put all 8 once against the 8 bits. So first 8, second 8, third 8, and for 2 to 4 we are having 1 1 1 and the rest 5 bits are zeros. Now our job will be number of masked bits in the last byte is m. Masked bits means how many ones, consecutive ones are there. So here it is clear, that is m is 3. And number of unmasked bit, that is number of zeros in the last byte, it is 5. So from here we can derive the number of subnets, so which is equivalent to 2 to the power m, where m is the number of masked bits, m value is 3 here. That's why 2 to the power 3, which is 8. So 8 subnets are there. Now number of IP address in each subnet, it will be equivalent to 2 to the power n, where already we have derived n. N is the number of unmasked bits. So 2 to the power 5, that is 32. So 8 subnets are there. In each subnet there will be 32 addresses. For the first subnet, so as the address is given here, 192.168.130.0. So starting with the 0, so if we plus 31, then it will be 192.168.130.31. This will be the first subnet. And definitely the second one will be started with 32. So that's why the second one is started with 32. Again we have to add another 31 because this is the one. So we are having rest 31 because in each subnet there are 32 addresses. So 32 plus 31, which is equivalent to 63. So we are doing so. We are calculating and we are getting this. And for the last subnet, so here is which is 192.168.130.224.2, and so add 31 only here, so we will get 192.168.130.255. And now from here again we are having some questions, that is we will check whether some addresses are belonging, their belongingness we are going to check, that is in which subnet they are belonging to. For the first one, 192.168.130.10, so definitely it is belonging to this range, first subnet, because their range is 0 to 31 and we are considering 10, so it is belonging to that range. And in this way we can find the belongingness of these given IPs checking this range of the subnet, each of the subnet. It is quite easy. And along with this, as with the normal addressing, we are having 2-level hierarchies, that is the net ID and the host ID. With subnetting, we are having 3-level hierarchies. Along with the net ID and host ID, we are having subnet ID as well. That is the net ID is again broken into 2 parts. That is the network prefix and the subnet prefix. And it is just like the telephone numbers, that is one country code will be there followed by the zonal code. So if we consider the earlier telephone numbers, so there this hierarchy is maintained as well. Another example to clarify more doubts with subnetting, and here the address is given 190.100.0.0/16, where /16 is the subnet mask, and the task is given, the first group we have to create, it will have the 64 groups, customers, and each of them will have 256 addresses. And in the second group we will have 128 customers, that is each customer will be given a block and they will have this number of addresses. And In similar fashion, for the third group, another 128 customers are there. Each of them requires 64 addresses. Now we are proceeding with this problem. For the first group, we follow each customer needs 256 addresses. So that's why the 8, this should be the masking bits we need. And 8 means masking bits means here 24 slash, because how we used to derive the m value, that is the number of subnets. M is derived with the number of masked bits, that is the number of consecutive ones present. So that's why here m value will be 24. And for each of the addresses you follow, for the first customer, it will have the 190.100.0.0/24 and up to 256, because started with 0 and 255, this range is covering 256 addresses, and this is true for all 64 customers. That is, from 0 we'll move to 1, then we'll move to 63. That is 0 to 63. It is covering the range of 64 customers, and in each customer they are requiring 0 to 255. You follow? For each of them 0 to 255. So this is the number of addresses required, and this second byte is representing the customer identification. Customer 1, customer 2, customer 3, and this is in case of group 1. And once again we are following the task given. That is, the first group will have the 64 customers and each of them needs 256 addresses. And for the second group and third group, we will proceed in the similar fashion. Here is group 2, where we are having 128 hosts and at the same time 128 addresses. So if we consider this one, only this mathematics will give us the number of masks. So log 2 128, so it is derived to leads to 7. So that's why only we have to consider 7 means how we are getting 7. Actually 32 minus n, it should be 7. So what should be the n value? It should be, definitely it should be 25. So in this way we are getting 25, and the mask should be 25 for all the customers. That is the first customers to up to 128 customer, and each of the customer will have 128 number of addresses. So 0 to 127. Again you consider 128 to 256, another 128s. So in this way we are getting the all the customers and their required number of IP addresses. And for the third one, in similar fashion, we can get, that is, here the each of these customer is requiring 64 addresses. So again you follow log 264. So what should be the value? Definitely it should be 6. And how 6 is derived? 32 minus n equals to 6. So mask should be of 26 bits. That is 26 plus 6. That is equivalent to 32. And here we have given first to 128 customer, and each of them will have the 64 IP addresses. Here you follow 0 to 63 and 64 to 128, and each of them is covering this range, 64 addresses. And whereas the number of customer is 1 to 128. Now here is end of my presentation, and if any question is there, then I am ready to clarify.